All right, so as I said, excuse me, today we will finish talking about electrophilic aromatic substitution. We'll talk about how to make this big molecule, which has something to do with strawberry soda. All right, so here we go. Let's review where we were last time. Electrophilic aromatic substitution, often abbreviated EAS, is a substitution reaction in which an electrophile attacks an aromatic ring. We've been talking about it in terms of benzene rings, but in fact the same mechanism operates on all many other aromatic rings. And this leads to replacement of usually a hydrogen atom. That's what we're going to see. Occasionally other groups can be replaced, but most of the time it's a hydrogen. Here is an example. If we take toluene and react it with bromine FeBr3, the FeBr3 is a catalyst. These guys together form an electrophile, the Br2 FeBr3 complex. There are three different positions in which the hydrogens on the benzene ring can be replaced. As it's shown here, the 4 o'clock and 12 o'clock positions are the same. Those are the ortho positions. Then there is the 6 o'clock and the 10 o'clock position, so to speak, relative to where the methyl is there. That's meta. And then directly across the ring from the methyl, that's the para. Now, the mechanism for this process, we start by making the electrophile. That's the reaction of Br2 with FeBr3, which is a Lewis acid, electron deficient. So we get a new iron-bromine bond, and that importantly puts a full positive charge on that middle bromine atom, making that Br2 more electrophilic, more reactive, capable now of attacking the benzene ring. In the absence of making it more electrophilic, the benzene ring is just too aromatic. It costs too much energy to climb that hill. So there's our electrophilic attack here, excuse me, showing the mechanism for the ortho product, but the meta and para product mechanisms look very much the same. We get a resonance stabilized carbocation, which then we consider carbocation fates. In this particular case, however, one carbocation fate dominates greatly over the others. That is a loss of a proton, B-deprotonated, because unlike the other carbocation fates, this one leads to the restoration of aromaticity. The combination of the resonance contributors that are formed upon electrophilic attack on the benzene ring is called the arenium ion, and we've seen last time that the arenium ion structure is important because it has to do with rate effects, activating, deactivating effects. It also has to do with directing effects, ortho, para, and as we're going to talk about today, meta-directing effects. Also, the step in which the electrophile attacks the benzene ring and aromaticity is lost, that is our rate-determining step. So when it comes to directing effects and rate effects, that's our step we're going to look at. Now, the fact that the methyl group gives mostly ortho and para products results in us calling the methyl group an ortho-para director. In other words, it directs the incoming electrophile to the ortho and para positions. It's also an activator, which means the reaction of methyl benzene with this electrophile is faster than the reaction of benzene itself with that electrophile. And so consequently, we call it an activator. That makes it faster. And both of these effects, the directing effect as well as the activating effect, come from the fact that a methyl group is an electron donor and a carbocation stabilizer. All right. Now, last time I left you to think about a different group attached to the ring, one which was not in our ortho-para director list, and that was a nitro group, NO2. Nitro groups show up quite frequently in electrophilic aromatic substitution, either as things already attached to the ring or something we add to the ring. And so if we take nitrobenzene and brominate it, we get ortho, meta, and para. The question is, which is the major product? That's going to be based on the directing effects. So to figure out the directing effects, we have to know the structure of the nitro group, that NO2. And so here it is. The wavy line just says that's where it's attached to the benzene ring. It's NO2 with this nitrogen positive charge, one double bonded oxygen, which is no formal charge, and one oxygen, which has a single bond and a negative charge. You can flip the position of the double bond through resonance. But either way, there's only two significant contributors. If you draw the contributor which gets rid of the positive charge with nitrogen, you end up with either 10 electrons on nitrogen, which is bad, or an oxygen with a positive charge and an open octet, which is also bad. So in other words, this is pretty much what you've got for a nitro group. So how does this influence the position of attack ortho, meta, para? In other words, how does this influence the carbocation stability? Well, let's look at the arenium ions that come from the ortho, meta, and para attack. This is exactly the same as we did for the methyl case. As a matter of fact, I generated this slide by simply taking the methyl slide and replacing methyl with nitro. So the curved arrows are going to look identical. There is the ortho attack, so the electrophile there, moving the positive charge around through resonance. Meta, same kind of thing, positive charge in 3 places. Para attack, again, 3 carbocations. Now, are 3 carbocation resonance contributors, 1 structure. We saw before that the resonance contribution of all these structures, which makes up the hybrid, that's going to control the relative stability of these carbocations. So to do the same analysis we did before, we're going to look at the individual contributors and analyze them in terms of is the carbocation methyl primary, secondary, tertiary, otherwise stabilized or not. They all have the same amount of resonance pretty much. So this guy is secondary. This guy is secondary. This guy is another secondary. The positive charge is on a carbon that only bears 2 other carbons, but it's right next to the nitro group. And it says up here, bad secondary, because the positive charge of the carbocation is right next to the positive charge of the nitro group. That's bad. So the nitro group certainly doesn't help in that way. Also, the nitro group is 3 electronegative atoms, 1 nitrogen and 2 oxygen, and those are taking electron density away through an inductive effect. Now, you can draw a resonance contributor in which you fill the carbon's open octet by swinging down the nitrogen-oxygen pi electrons to make a nitrogen-carbon double bond, but that gives this oxygen, the 10 o'clock oxygen up here, if you will, that gives that guy an open octet and a positive charge. And it is even worse to have an open octet and a positive charge on oxygen than it is to have an open octet and a positive charge on carbon. So the net effect is the nitro group does not add any more resonance contributors. It doesn't provide new resonance contributors that provide extra stabilization, and its electron withdrawing inductive effect makes this positive charge. It amplifies this positive charge. So overall, that's not a good contributor. Let's throw it out. Let's not consider it. It's not of any major importance. In the meta case, we have a secondary contributor, and another secondary carbocation contributor. And none of these have the nitro group immediately next door. Now, every quarter somebody says, but isn't the nitro group affecting the positive charge regardless of where it is on the ring? That is true. Inductive effect matters everywhere on the ring. It decreases with distance. But all of these positive charges have that. The same thing up here in the ortho case and the same thing in the para case. So they all feel that inductive effect, but we're looking for differences because we're trying to make a comparison. In the para case, we have a secondary. We have a bad secondary. Again, positive charge next to the nitro group. Let's throw that one away. And another secondary. All right, so if we want to put all these together, think about the hybrids for these 3 attacks, ortho, meta, and para, because remember, it is the hybrid that's going to tell you the overall structure. That's going to tell you the relative stability of these cations. The ortho case has positive charge mostly on these 2 carbons, the 4 o'clock carbon and the 7 o'clock carbon. This structure really doesn't count. In the meta case, we have the positive charge delocalized over 3 carbons, 2 in the ortho case. And the para case really only has delocalization over 2 carbons. So in other words, the meta case carbocation or rhenium ion looks better, has more stability because the charge is delocalized over more carbons. So based upon that stability, the meta carbocation, the rhenium ion formed by meta attack is more stable, so that should be the major product. So our prediction here is meta, and then we're going to put ortho greater than para in terms of product for exactly the same reasons we talked about last time, probability and steric effects. The nitro group and the bromine that are coming in are not necessarily so large as to make the steric effects outweigh the probability. So ortho has 2 positions, para has 1, so we'll put ortho greater than para. So that's the prediction. Meta, more meta, some ortho, little or no para. Now, if we go into the lab, that's actually what we see. Meta is the major product. And consequently, we call the nitro group a meta director. It directs the incoming electrophile to the meta position. Why? Exactly the same reason as the ortho-para directors. It's an issue of rhenium ion stability. The nitro group destabilizes carbocations right next to it, which happens from ortho and para attack. So meta attack is favored. This does not come from carbocation stabilization, the way that orthoparas work, but actually it comes from carbocation destabilization. So it's kind of a punitive effect. It's not saying meta is good because I'm going to make because I'm going to improve the carbocation stability there, but rather the nitro group says ortho and para are bad because that's where I'm going to hurt you. And in ortho-para director, ortho and para attack led to stabilized carbocations, whereas meta attack just was a carbocation. All right, now by extension then, because the nitro group's directing effect is coming from carbocation destabilization, then we would predict by extension that any carbocation destabilizing group should be a meta-director. So we can make a list of meta-directors. Now the meta-directors will look more kind of miscellaneous. They're not as easy to categorize as the ortho-para directors. And they are things like nitro, which we just talked about. They are things like nitrogen with a positive charge next to the ring. So these no longer have a lone pair to do the resonance, donation, and stabilization. They have that positively charged nitrogen, which is even more electron demanding than a nitrogen normally is. We have a carbonyl next to the ring. Any carbonyl containing functional group, as long as that carbonyl is directly bonded to the benzene ring, is going to be an electron withdrawing group. So that's what I mean, the carbonyl directly attached to the ring. Now you might say, wait a minute. Did we not say before, when we talked about ortho-para directors, that having a pi bond, carbon-carbon, double bond, triple bond, benzene ring, having those next to the benzene ring stabilizes the carbocation because it adds extra contributors. So what's different in this case? Well, the difference in this case is one particular contributor. If we move, well, let's say there's a methyl out here. If we have this guy, E for electrophile, there's our H. And so let's suppose we get that irenium ion that comes from ortho attack. We can draw a resonance contributor in which the carbonyl pi bond electrons are moved down to satisfy the positive charge on the carbon. But what does that leave? Well, we had two lone pairs to begin with. We still have two lone pairs, but now a positive charge on the oxygen. So I took the electrons from the pi bond and folded those down. So between these two contributors, which one is better, the carbocation contributor or the oxygen cation contributor? Which one is more important contributor? Left guy on the left or on the right? What's the difference? They both have open octets. Here open octet on carbon, here open octet on oxygen. They have the same amount of bonding, they have the same number of electrons, et cetera, et cetera. The difference boils down to where does the positive charge reside? Carbon or oxygen? Which can deal with a positive charge more effectively? Carbon. So this is the major contributor in that way. And that doesn't mean that this isn't contributing, but there's something else you have to remember. This oxygen, being electronegative, is sucking electron density towards itself. This is an inductive effect. And that's still operating here. So the carbonyl is doing two things to the carbocation. It's providing electron density through resonance, but it's taking it away through the inductive effect. And as it turns out, the balance of factors is such that the resonance effect is virtually unimportant. Oxygen with an open octet is really never of any importance. So that contributor is virtually no value, no significance whatsoever, so we're left with the inductive effect. And that destabilizes the carbocation. So that's why a carbonyl group is a meta-director, because it destabilizes. The net effect is to destabilize the carbocation. Carbon-nitrogen triple bond, also a meta-director for exactly the same reason as the carbonyl. A CF3 group. Now, CF3, you might say, well, that looks like an alkyl group. But remember that alkyl groups like methyls are not very powerful electron donors. They're weak electron donors. It's like if you think of the carbon that bears the positive charge and everything it's attached to it, the carbon that bears the positive charge is you when it comes to pay rent. And if you have to pay rent, let's suppose you live in Westwood, so your rent is, what, $3,000 a month? So if you've got 3 hydrogens attached, you have to pay that rent all by yourself. The hydrogens don't help. If you have a methyl group attached, you still owe that $3,000 rent, but the methyl group is like a roommate who adds $10 to the rent. Okay, so instead of paying $3,000 out of your pocket, you pay $29.90. It doesn't help much. It helps a little bit, but not much. The problem here with the CF3 group is the 3 fluorines are working in the opposite effect. They're taking electron density away, and they easily overwhelm that poor carbon's ability to donate electrons. So the net effect is the inductive effect of the 3 fluorines makes the CF3 a meta-director. A sulfonic acid, that's a guy that has, the structure's not drawn up here. We'll see this later. A sulfonic acid looks like this. Here's our benzene ring point of attachment. And this has electron withdrawing effects pretty much exactly the same way as a carbonyl does. And there are others as well. Now, how do you identify these guys? A good way to try to identify, to look at a group and say, is this an orthopara or a meta-director? Well, these are kind of miscellaneous groups. But the ortho and para directors were all carbocation stabilizers. So a good way to do it is to say, is this or is this not an ortho-para director? If not, then it's got to be a meta-director, because that's your choice, orthopara or meta. There aren't any groups otherwise. All right, so in general, if it destabilizes a carbocation, it is a meta-director. Now, what about rate? We talked about before about methyl groups and things like that being orthopara directors, and notice that not all, almost all, orthopara directors are also activators. The exceptions were halogens. So let's look at nitro. Well, again, the rate-determining step, since we're looking at the rate of the reaction, we have to find the rate-determining step, and that is the reaction of the electrophile plus the nucleophile to make the irinium ion. The electrophile is going to be the same in both cases. It's the Br2-FeBr3 complex, so that's not a difference. What is different is the benzene rings, and we have the effect of the nitro group. Well, nitro, as we've seen, is electron withdrawing because of all those highly electronegative atoms, and the nitrogen with its positive charge sucking electron density out of the benzene ring. In the benzene case by itself, we have just hydrogens, and as we've mentioned before, hydrogen is neither electron withdrawing or electron donating. It just kind of sits there, doesn't help, doesn't hurt the situation. All right, so what about nucleophilicity then of the benzene ring? Which is more nucleophilic, nitrobenzene or benzene by itself? Which has more electron density in the ring? Nitrobenzene or benzene? Benzene does, right. So benzene more nucleophilic than nitrobenzene. The nitro sucking electron density out. Now, we also said that we can look at the irinium ion stability. That's something else that matters. Remember, the more stable the product of the mechanism step, the faster that mechanism step tends to be. So we look at the irinium ion stability. The nitro, again, is an electron withdrawing group. That certainly does not help the stability of a carbocation. It's hurting it, as a matter of fact. Hydrogen, again, doesn't help, doesn't hurt. So we end up with 2 irinium ions, similar in structure. The plus means the charge is distributed over that carbon, by the way. You could draw the delta pluses on the other carbons if you'd like. It's just more convenient for this drawing to do it that way. So the nitro group is making this carbocation more electron poor through its electron withdrawing effect. So which one of these 2 carbocations is more stable? The one derived from nitrobenzene or the one just derived from benzene? The one just from benzene, because it doesn't have that sucking effect out here, so to speak. And so the benzene-derived irinium ion more stable than the nitrobenzene-derived irinium ion. This is good because these 2 effects then are synergistic. The nitrobenzene not only is a poorer nucleophile because of the electron withdrawing effect of the nitro group, but also leads to a less stable irinium ion because of the electron withdrawing effect of the nitro group. So the 2 of those together leads us to the conclusion that the Br2-FeBr3 reaction of nitrobenzene with benzene is nitrobenzene. Is this going to be faster or slower? Slower, because it's a less nucleophilic ring and a less stable carbocation. So therefore, the nitro group is a deactivator. Slows things down. Now, at this point, when we were talking about the toluene case last time, we said, does this mean that ortho-para directors are all activators? So we should ask the same question here. are all meta-directors, deactivators? And the answer is yes. There really are no exceptions, at least no common exceptions to that. There are rare exceptions, but we're certainly not going to run into them in here. All right. So what that basically means, I don't have a slide for this, but what that basically means is our attachments, our substituents on the benzene ring can be divided into three categories. Orthoparadirectors that are activators, orthoparadirectors that are deactivators, and then metadirectors that are deactivators. And if you want a little bit more on that, go read the Okatsa chapter. It goes through that whole argument. And if you don't have access, send me an email and I'll tell you how to get there. All right, now what we're going to do is move away from the mechanism and the kinetics and the directing effect and look at different electrophiles. Electrophilic aromatic substitution is good for more than just replacing a hydrogen with a bromine. There's a huge number of different things you can put on the benzene ring. This actually is one of the most prevalent reactions we use for putting new substituents on a benzene ring. So we're going to look at those, and we're going to see some patterns that come out of this. So let's start by looking at bromination, but I want to look at it slightly different so we can begin to see these patterns. So the overall change we want to make here is take a hydrogen attached to an aromatic ring. That means AR is abbreviation, common abbreviation for aromatic ring. We don't mean argon here. And we're going to change that to a bromine. So the electrophile, and for these couple of slides here, I'm going to put the electrophile in a red box so we can identify it. The electrophile comes from Br2 reacting with FeBr3 to make that complex. That's the electrophile. Or we can also take that complex and ionize it apart. Remember, this bromine-bromine bond has been weakened because we now have a better leaving group. So we can ionize that away and make the Br plus and use that for the electrophile that attacks the benzene ring. Now, in the laboratory, the one that's actually operating is a function of a whole lot of things, temperature, other conditions, etc. But on paper, for our purposes, it doesn't matter whether you use the Br2 FeBr3 complex that we've been talking about, or you can use Br plus if you like. All right. Here's an example of bromination. Of course, we've been talking about this kind of reaction, but here's a different one. This is aniline, benzene ring with an NH2 on it. And the products shown here are ortho and para. So let's first of all try to figure out why is NH2 an ortho-para-director instead of a meta-director. Why should this guy, this trick never works, why should this guy here and there, hint, hint, why should that guy, NH2, be an ortho-para-director? What does an NH2 group have there and there? It's a lone pair. When a group has a lone pair on the atom next to the benzene ring, is that an ortho-para or a meta-director? It's an ortho-para-director. They all stabilize carbocations. Now, this happens to be an activator. Not everything which has a lone pair next to the benzene ring is an activator. They're all ortho-para-directors, and except the halogens, they're all activators. So this is an activator, an ortho-para-director, so we get ortho and para. And which between those two, ortho and para, do you think is the major product? Is it ortho or para is major? Well, when we're not talking about ortho-para versus meta, the other two factors when we're not talking about arenemine stability, which is the lone pair, the other two factors we talk about are location, 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 right? And so the number of positions available as well as steric effects. And in this case, the NH2 and the Br are not really big, so the number of positions, wins out, and so we predict ortho to be the major product. Now, in the laboratory, it may actually be para is greater than ortho because there's a number of other factors that influence it. The balance between number of positions and steric effects can be very, very fine. Sometimes if you run the reaction at one temperature, you get a certain ortho to para ratio, but if you heat it up, say, 10 or 20 degrees higher, the ortho-para ratio changes. So we're not going to worry about that. We're simply going to assume about the arenemine stability, the number of positions, and the steric effects. All right, and again, for practice, write out the complete mechanism by yourself. All right, let us imagine we wanted to put a chlorine on the benzene ring. So replace a hydrogen with a chlorine. By parallel with what we just did, I mean, bromine and chlorine are in the same column of the periodic table. They have a lot of similarities, especially in their mechanisms, and so we might predict, let's just use Cl2 instead of Br2. That's a good prediction. because it turns out we can take chlorine. Now, aluminum chloride works better than iron chloride, but you could still use iron chloride if you like. But aluminum chloride works the same way, has an open octet, takes a pair of electrons from the chlorine to make this guy, Cl2AlCl3 complex, which is a powerful electrophile for the same reason as the Br2FeBr3 complex is. So there's our electrophile. Or once again, we can ionize the halogen-halogen bond to make the Cl+. That can be the electrophile. Here's how we might use it. Let us imagine we have this molecule, which is called xylene, in this case meta-xylene. Benzene with 2 methyl groups on it is xylene, and there's 3 isomers for that, so this is the meta-isomer. And if I put chlorine on there, I can put the chlorine, as it turns out, one of 1, 2, 3 places. Now, 2 products are shown here, so let's analyze those possibilities. First of all, let's think about the directing effects of methyl groups. Are methyl groups orthopara or meta-directors? Hint, what do methyl groups do to carbocation stability? They improve carbocation stability. So are methyl groups orthopara or meta-directors? They're orthopara directors. So that means that this methyl group right here is directing to this position, that's an ortho. This position, that's ortho. So 2 o'clock, 10 o'clock, and 6 o'clock. That's where this guy is directing. This methyl group is directing to 6 o'clock and 2 o'clock. Those are the 2 ortho positions. And 10 o'clock. That's para to this methyl group. Now, if you've drawn little stars in your think book, you'll notice that these 2 methyl groups are working together. Their effects are synergistic. They're both directing to the same 3 carbons. So this carbon right here, the one in the 8 o'clock position, isn't being directed to, so the electrophile doesn't go there. So that leaves us with putting the chlorine in the 10 o'clock position, the 6 o'clock position, or the 2 o'clock position. Now, why don't I have it drawn in the 6 o'clock position? Well, because that's the same as drawing it in the 10 o'clock position. If I have it here in the 6 o'clock position, it is ortho to one and para to the other. When I have it drawn in the 10 o'clock position, it's ortho to one and para to the other. So 6 o'clock or 10 o'clock, exactly the same. But notice there are 2 positions that lead to that combination. This guy, there's only one position that puts the chlorine between the 2 methyls at the 2 o'clock. And so those 2 facts together should allow us to predict which one of these is the major. Chlorine, the first one, or chlorine not between, or chlorine between, which is the major one? Well, let's see. This guy has 2 possibilities that lead to this isomer. This only has 1. There are 2 positions that put a chlorine ortho to one methyl and para to the other, but there's only 1 position that puts the chlorine between the 2 methyls. So the probability, the number of positions, favors the first one. What else do we think about as well? We've talked about irenium ion stability. That's where the orthopara directing effects come from. We've talked about probability, and the third thing we talk about is steric effects. So everything else being equal, would you rather park your car between 2 big cars or next to 1 big car and 1 little car? In other words, is it easier to put the chlorine next to 1 methyl or next to 2 methyls? Next to 1 methyl, because it's less crowded. So there are 2 things, 2 features, which make this first product that's listed the major one. Probability, number of positions, as well as steric effects. And that, in fact, is our major product. And you can write out the whole mechanism to get some practice with that. Now, you may have noticed in these 2 examples, bromination and chlorination, that there is a pattern. And if not, when we talk about more electrophiles, hopefully the pattern will develop for you. Here is a useful way of remembering, of figuring out what the electrophile is that's going to attack the benzene ring. In the bromination case, this was our product, our major product, ortho-bromoaniline. And this came from, now here's what I'm going to do. This is the same thing, and I'm going to show you the trick for remembering. What we're going to do is erase the bond between the benzene ring and the electrophile and give those pair of electrons to the benzene ring. So here we go, erase. Let me show that again. Erase. What that tells us is that this molecule comes from that benzene ring plus Br plus, or something related to Br plus, as the electrophile. In the chlorination case, that's not to be confused with coronation. That's what gets done with kings. That came from Again, there's our product, but if we erase the carbon-chlorine bond and take the electrons away from the chlorine, Cl+. Now, that may sound kind of trivial to do it that way, but what it's saying is, in general, when I have a benzene ring and I've added something to it, that comes from, again, erase the bond and give the electrophile usually, not always, we'll see one exception to that, but the electrophile usually has a positive charge. So this means when you're trying to figure out what to mix together or what the mechanism might be, there's your clue. Cover up the carbon or the benzene ring to new group bond, put a positive charge on the new group. There you go. All right, let's see how that operates by talking about putting a nitro group on. Putting nitro groups on is pretty common. As a matter of fact, this is one of the best ways to introduce a nitro group into a molecule is through electrophilic aromatic substitution, especially if you're making TNT. That's how it's manufactured. So is Wile E. Coyote in the audience today? I know he likes TNT. He has such bad luck with it, I don't think he'd want to make his own. It turns out to be you have to kind of force that third nitro group to get on there, but it's not like it blows up when you make it. All right, so what do we want to do? We want to convert a hydrogen into a nitro group. Use the same trick. Erase the benzene ring to NO2 bond, give the NO2 a positive charge. There's the electrophile. NO2 plus is what we're going to use. Draw it a different way. That's the most significant resonance contributor. Where does that come from? Well, there's a couple of places you might think about it coming from, but especially if you're thinking about chemistry on a really big scale, an industrial scale, where you're going to try to use things that are cheap, nitric acid, that's nitric acid. That's a good source. Now, how do we go from nitric acid to NO2+? We have to take away an OH group. Can OH leave? Have we run across the special circumstances where OH can leave yet? I'm here to tell you this is not one of them. We won't see that until we get into carbonyl. So no, it can't leave by itself. Fair enough. How do we make an OH into a leaving group? Put a proton on. So we need a strong acid like H3O+, which, by the way, comes along with the nitric acid. Nitric acid is usually aqueous. So we put the proton on there, and then we can have it leave. I'm using this resonance contributor at the same time because otherwise, if the water just leaves, we end up with a nitrogen with a 2+ charge, really bad. So this gets around that. There's our NO2+ cation. Now, often when we have this discussion, people say, but you're putting the proton on the neutral oxygen. Here's a negative oxygen. Shouldn't we be putting the proton on the negative oxygen, like so? And the answer is no. Why is this not as good a thing to do as this? Resonance, absolutely. Did you just wake up and said resonance, or were you actually paying attention? There's resonance between the N+ and these two oxygens. There's some out here, but this is more important. If you put the proton on here, you don't disrupt that, but if you put the proton on the O-, you lose that. You lose resonance. So this is not as good because you pay a resonance price. You can still do it. You can still push through the curved arrows. Just doesn't happen that way. All right, here's an example. Let us suppose you wanted to nitrate bromobenzene. There's bromine. So we use aqueous HONO2. That's nitric acid. Oftentimes you'll see nitric acid written as HNO3. That's also fine, but I'm writing it out this way so that you can remember this structure. We need a proton source as well, aqueous H2SO4. It's a very nasty, nasty combination of things. Two strong acids. So that puts the nitro group on. The bromine is an ortho-para director. It has lone pairs. And so we get ortho and para. And of course, ortho is the major one, again, because there are two ortho positions and one para. This, by the way, is a great example of how this particular reaction, we're talking about ortho-para ratios being sensitive. If you run this reaction at room temperature, it's like 70 to 30 or something like that. And if you heat it up, it becomes closer to 1:1. But it's still generally more ortho than para. And again, write out the mechanism for yourself to see how that works. Now, let me go back to this one slide here. You may have said, wait a minute, I don't understand something here. Here we're got this nitrobromobenzene product, and you're saying ortho and para is major. If you go back to the beginning of today, when we talked about nitro group, we said that meta is major. I don't understand. We have bromine and nitro. How do we get ortho and para in one case and meta in the other? So the question we have to ask is just who is in charge here? Well, If we, to summarize what I said, if we take bromobenzene and nitrate it, we get ortho and para. Because bromine's an ortho-para director. If we take nitrobenzene and brominate it, we get isomer, but now meta is the major product. Now, the reason I'm bringing this up is because we have to remember that in general, when we have an electrophilic aromatic substitution reaction where we have some group, let's just call it G, already attached to the ring, it is the group G that's already attached to the ring that influences the rhenium ion stability. It is not the electrophile that's being added. So in this first case, in the nitration of bromobenzene, the bromine is already attached to the ring. It's an ortho-para director. In the nitration case, or excuse me, the bromination case, the nitro is already attached to the ring. It is a meta director, so we get a meta product. Now here's another way to think about it. Here is a director and an actor, well, a guy dressed up. This is George. This is from Star Wars, by the way. I don't mean the original 1977 Star Wars, where if you watch it now, you laugh because you can see the cutouts of the TIE fighters moving across the screen. With all due respects to Mr. Lucas, if he's watching the video today. There's Lucas. He's the director. There's the guy, I forget who it is, who's dressed up as C-3PO. Now, who in this scene is telling who where to go in a polite way, right? This is the guy that's already attached. He's the director. He tells the actor where to go in the scene. So the thing that's already attached to the group, or the ring, that's who's in charge. That's who the director is. All right, let's do another electrophile, sulfonation, making a sulfonic acid. Sulfonic acids tend to be not important so much when they're attached to sp3 carbons. There's examples of them, but they're really important when they're attached to benzene rings because what they do is they tend to add water solubility. So we'd like to know how to put them in. So we're going to use the same trick. Erase the AR bond and put a positive charge on the sulfonic acid. That's what we get. We can draw it out like that. You can also draw it out in another way that's not shown up here. You can draw it with a positive charge on the sulfur and an OH single bond. Where does it come from? Well, it turns out a really easy way to make it is to take sulfur trioxide and put a proton on. There you go. That's the electrophile. Now, as it turns out, you can also use SO3 by itself. Sulfur trioxide by itself is sufficiently electrophilic for that to happen. This sulfur in the middle has got a lot of delta plus on it. And let me give you a metaphor. How many of you watch Big Love on HBO? Anybody know that show? That's the polygamous show, right? Oh, come on, you can fess up. Actually, I watch the show. Because it makes me glad I only have one wife, let alone three. But anyways, in this show, Bill Paxton plays a polygamist whose 3 wives now this season are fighting amongst each other because they're all jealous, et cetera, et cetera. And wife number 4 is going to come in and make things even more complicated. And, of course, his children are pulling him every which way, et cetera. So here's how the metaphor works. See this sulfur in the middle? That's the husband. The 3 oxygens, those are the wives, right? So this poor sulfur is having its electron density taken away by not 1 oxygen, but 3. And that sulfur is really electron poor. Big delta plus on that sulfur. So sulfur trioxide by itself, sufficiently electrophilic, often to attack a benzene ring. All right, so here's an example. Let's in this case, put the sulfonic acid on with a ketone. A ketone, as we said, is a meta director for this reason we talked about up here. And so there's the sulfonic acid on there. Again, I'll let you work out the whole mechanism for yourself as a lot of practice. You may notice in the process of working out these mechanisms that there are parallels in all the mechanisms. They tend to have the same 3 features in them. Step 1, make the electrophile. Step 2, make the rhenium ion. Step 3, deprotonate the rhenium ion. All right. How about if we want to put carbon-carbon bonds on? We've talked about making all sorts of other bonds, but what about carbon-carbon bonds? This is a particularly important process because when we're building more complicated molecules from the simple molecules that Mother Nature gives us, many times we have to make the carbon skeleton more complex, and electrophilic aromatic substitution turns out to be a pretty good way to do that. So what we want to do is replace a hydrogen with some sort of alkyl group. So what would the electrophile be? Well, erase the AR, put a positive charge in the alkyl group. An R group with a positive charge, say a CH3 plus with a positive charge, is a carbocation. Do we know how to make carbocations? Yes. Turns out there's lots of ways to make carbocations. There's one in particular that works really well for this. We can use, again, our friend aluminum chloride. In this case, we're going to improve the leaving group ability of the chlorine. Now, chlorine can leave by itself, but this will help the process, especially when the R group doesn't lead to a really stable carbocation. So we get this complex, which looks a lot like the ClClAlCl3 complex. And that can ionize in the same way to make a carbocation. Now, either of these guys, the complex or the carbocation itself, can be the electrophile that attacks the benzene ring. It really depends upon the stability of the carbocation. When the carbocation is less stable, say it's methyl or ethyl or something like that, then this is our electrophile. But when the carbocation is more stable, tertiary, resonance stabilized, that kind of thing, then it will tend to be the free carbocation. And because this is a carbocation process out here, all the usual carbocation fates operate, especially rearrangements are possible. Here is an example, by the way. This is called the Friedel-Crafts alkylation. Alkylation because we're putting on alkyl groups, and Friedel-Crafts because those are the Frenchman and the American who discovered this process in the 1870s. Here is an example. Let us imagine we wanted to convert benzene to tertiary butylbenzene because we are trying to have better aviation fuel so we can win the Battle of Britain. This was actually a piece of technology that helped the Allies win World War II. Because when you have more alkyl groups on your aromatic rings, you get higher octane rating, which you definitely need for airplanes. So how would we put that on there? Well, let's do that same trick. Take this guy, erase the benzene ring, put the positive charge, and what are you left with? Tertiary butyl carbocations. What we need to do is to make the tertiary butyl carbocation by this trick where we rip the chlorine off a tertiary butyl group. Now this is, you can generate the carbocation by any other carbocation generating method. Protonating a pi bond, that kind of thing. Those will also work as well. This just happens to be one that works particularly well with the benzene ring. And again, write out the whole mechanism for yourself. We can also put carbonyl groups on a benzene ring with a related reaction called the Friedel-Crafts acylation because we're putting on an acyl group. So the electrophile here, again, erase the AR group and we end up with this carbocation. You might say, I don't know if I like that carbocation because it is primary. It might even be less than primary if R is a hydrogen, but that turns out that's too unstable to make. But you can make this with R equals just a methyl. Why? Because this is not just a primary carbocation. It's primary with resonance. We can use the oxygen lone pair to make this. And you might say, whoa, 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 whoa. 3 bonds to oxygen? Does that look weird? It shouldn't look that weird. We've been using 3 bonds to oxygen ever since you were in high school or before, right? If you were one of those, special children that took chemistry in 2nd grade, how many of you took chemistry in 2nd grade? All right, 3rd grade. Really? Nobody? Every year somebody says, yeah. No? All right, never mind. But you've been using oxygen with 3 bonds and a positive charge for a long time. In what form? Hydronium ion. Nothing wrong with oxygen with 3 bonds. Here they happen to be pi bonds, but you can have an sp oxygen. Works just fine. So this is a pretty happy cation. It's called an acylium ion. And how do we make this? Well, same old trick we've been using. Rip a chlorine away. In this case from an acid chloride. Put the aluminum chloride on to rip it away, and we get our acylium ion. You might see patterns there in electrophilic aromatic substitution of stealing chlorines. And there's our electrophile. So how might we use it? Let us suppose that we wanted to synthesize this molecule that's here from this guy. This is called anisole. So we want to put the acyl group on para to the methoxy. It's an ortho-para director, so it'll work well. And it's kind of big, so maybe it'll favor para more than ortho. Well, use the same trick. Our electrophile, erase the benzene ring, positive charge in that carbon. There's the acylium ion, so we put a chlorine on there. And that's where our electrophile comes from. Once again, work out the whole mechanism, which is just a variation on that same 3-step. Make the electrophile, attack the benzene ring, deprotonate process we've been talking about. Now, there's one other electrophile I want to talk about before I talk about an application of all this, and that is this guy, putting a nitrogen-nitrogen double bond between 2 benzene rings. This may be kind of exotic, and it actually is kind of exotic. but it has one particularly important application. When we have a benzene ring, a nitrogen-nitrogen double bond, and a benzene ring all conjugated together, lots of conjugated atoms tends to lead to color. A lot of dyes are based on this particular structure. All right, so where does it come from? Well, once again, erase the aromatic ring. What you're left over with is the positive charge on that nitrogen. There's our resonance contributor. This is called a diazonium cation. The azo is nitrogen, so it has two nitrogen. And where does it come from? Here's where it comes from. It comes from an NH2 attached to a benzene ring, reacted with sodium nitrite. The stuff that we used to put in hot dogs to make them have a smoky flavor, but then we took it out because it was a carcinogen, but now it's back in because it's not so bad a carcinogen. And because people like their smoky hot dogs, right? What would a Dodgers game be without, a cancer dog? Actually, they put other stuff in now, but that converts the NH2 to N2+. How that happens, I'm going to leave that up to you to work out. There's an owl's problem. Now, this is an important mechanism for you to try on your own. The reason it's an important one is because if you can work out this mechanism on your own, you are definitely thinking along the right ways of learning how to do mechanisms. There's nothing in this NH2 to N2+ mechanism that you really haven't already identified. It's resonance and leaving groups and proton on and proton off and that kind of thing. So I'll leave that for you to work on your own. All right, here's an example. Let's imagine you wanted to make this molecule, which happens to be yellow, and you wanted to make it from phenol. So there is the bond that you would break. There's our electrophile. And that would, by using this process, would come from the NH2. And again, I will leave you to work out the whole mechanism for yourself to do that. Now, in our last couple of minutes, I want to talk about kind of an application of some of the ideas we've talked about, including this diazo, to make this molecule. This is called Allura Red C, and as the name implies, it is a red dye. It's an azo dye, and azo because it is the nitrogen-nitrogen double bond, colored because it is very extensive conjugation. You can count the number of conjugated p orbitals that are together there. This particular guy happens to be used as a food coloring. It makes this strawberry soda color, or cranberry juice, if you like to drink that. Tends to have some of this in it. Unlike a lot of other azo dyes, which have been banned for food use, this one's probably not a carcinogen. This nitrogen-nitrogen double bond seems to cause some trouble. Nonetheless, many dyes are azo compounds. They have this nitrogen-nitrogen double bond in which links a couple of aromatic rings, so we get lots of conjugation. All right, let us talk about where this might come from. It comes from that azo coupling process that we just talked about on the last slide. So this is the molecule, and it's a sodium salt of these two sulfonic acids because that improves water solubility. So it would actually come from this two sulfonic acids, and that's really the molecule that we're interested in talking about making. How would we make this? It's got a nitrogen-nitrogen double bond between two aromatic rings, so that suggests electrophilic aromatic substitution, azo coupling. So one of these guys has to be the nucleophile, one of these guys has to be the electrophile. It turns out it's easiest to use this guy for the electrophile and this guy for the nucleophile. All right, so where this comes from, well, the N2 was the NH2. That we've talked about before. This is the guy I want to talk about in terms of where the electrophilic aromatic substitution happens. There are two benzene rings, so we could attack either one of them. One has the sulfonic acid group on it, and is the sulfonic acid group going to be electron donating or electron withdrawing? It's electron withdrawing. So that hurts the nucleophilicity of this ring. That's electron withdrawing group. Over here we have an OH, which is electron donating because the oxygen has lone pairs. It's an ortho-para director, so that's an electron donor. So we have two rings. The one on the left is less nucleophilic because it's more electron poor. It has that withdrawing group on it. The one on the right is more electron rich because it has the donating group. That means if you're an electrophile and you sidle up to this molecule and going, hey, you've got electrons. I'm electron deficient. Let's make a bond. Oh, wait. I could react here or here. It's like twins. Right? If you're going, hey, here's two twins. Which one should I date? You can go as far as you like with that metaphor. This ring, this twin, is more electron rich. It looks better to the electrophile. So that's where the electrophile is going to go. Now, if we look at our reaction, we see that it's going to go in this carbon. Why this particular carbon? Well, the OH is an ortho para director, so it's directing into the ortho and para positions. That para position is blocked, but there's two orthos. Now, while this ortho position is where it goes, that looks a little bit more sterically hindered, but maybe there's some advantage to it. So what I would like for you to do when you think about this is to draw the arenium ion that comes from electrophilic attack there and see how it's better than the other ortho position. All right, next time on Wednesday we'll start talking about radicals, and for that we do not need our lecture supplement. We'll just do chalkboard for that one, so we'll see you on Wednesday.